Now the series grouping in capacitors in terms of what it means is exactly the same as resistors. So you would think at this point, because in this combination resistors, the equivalent resistance was the sum of all the resistances. So the way we deal with capacitors and the way we deal with resistors is going to be opposite, but the voltage about each one remains the same. V1 remains equal to V2 remains equal to V3. So the effective capacitance is just 3 plus 2 microfarad, that is 5 microfarad. Now in most cases this is what will be provided to you in the question, the points about which you need the equivalent capacitance. Hi students, welcome to Infinity Learn by Sri Chaitanya. Today we are going to be learning about the combination of capacitors. Now capacitors, just like resistors, can be connected in series or parallel, which means we can get the equivalent capacitance of multiple capacitors together. So let's see what the formulas would be and how to deal with them, what kind of charges and voltages they would take up based on how they are grouped together. First off, we learn about the series grouping. Now the series grouping in capacitors in terms of what it means is exactly the same as resistors, because in series grouping, as you can see, all of these capacitors are connected along the same wire. There's no branching in between. They are the same wire passing through each of the capacitors. And over there, the charge remains conserved. With resistors, this was the current remaining conserved. Over here, charge remains conserved because whatever charge comes in, the same charge must go out. So charge is conserved, but these potentials are different, V1, V2 and V3. Again, very similar to resistors. So V is equal to V1 plus V2 plus V3. So you would think at this point, because in this combination, resistors, the equivalent resistance was the sum of all the resistances. But over here, it's going to be a little different. And the reason is that for the current, you had V is equal to IR, which means V was directly proportional to R. But when you deal with capacitors, then you have Q is equal to CV, which means this C is inversely proportional to V. So the way we deal with capacitors and the way we deal with resistors is going to be opposite. Because when capacitors are connected in series, their equivalent capacitance is given by the reciprocal sum. This kind of formula we saw for resistors when they were connected in parallel. But for capacitances, this is the formula when they are in series. Okay? Because V is inversely proportional to the capacitance. So it's effectively coming from there. This is equivalent V is equal to V1 plus V2 plus V3. Since V is inversely proportional to C, that is from where this relation comes. Next up, we have if we have two capacitors, then the equivalent is C1 C2 by R1 plus R2. We saw this in resistors with regards to two parallel resistors. Here they have to be connected in series. Now V1, the voltage across the first one, is C2 by C1 plus C2 into total voltage. Be very mindful of this. When you're finding the voltage about the first resistor, it is V by C1 plus C2 into the second capacitor, the other capacitor. Similarly, when you're finding V2, it's V by C1 plus C2, which in a way is the unitary method formula, but you multiply with the other capacitance, not the same capacitance. If you recall, in parallel, when we were finding the current, then across two resistors which are in parallel, then it was always the other resistance divided by R1 plus R2 into main current. A similar thing applies over here as well. There what was different? Currents were different. Here voltages are different. So that is why we're finding the voltages here. So here we have the equivalent capacitance. If there are n number of equal capacitors, then the equivalent would be C by N, and your voltage across each one would be V by N. Moving on to the parallel grouping. In parallel grouping, your charge is split up. So whatever charge comes in, that is split up. But the voltage about each one remains the same. V1 remains equal to V2 remains equal to V3, and that is equal to whatever is the external voltage here. But the charges are different, and the net charge is the sum of each of these charges, again because of the conservation of charge. In this case, you will deal with it the way you deal with resistances in series. So remember, capacitance and resistors behave oppositely. What is the formula for series in one is the formula for parallel in the other, and vice versa. Okay. So Q is proportional to C. If you have two capacitors, then C is equal to C1 plus C2 expected. But when you're finding charge, then this time Q1 is equal to C1 by C1 plus C2 into Q. It is different from the voltage case. If we were finding the voltage in that series combination, then V1 would have been proportional to C2. But here in the parallel grouping, the charge on each is proportional to C1. How do you remember this? Remember, capacitance is the capacity to store charge. So whichever has more capacity will be able to store more charge. Okay. Again, here you have the total net capacitance for n identical capacitors as NC. Just add C n times, and the charge on each would be Q by n. Okay. Next up, if it's a complicated network, then how do we solve capacitive circuits? Same way as we did do for resistances, which means we try to find combinations of this is series, this is parallel, and if there are multiple series parallel together, then you have to go step by step. So what are the steps? First up, we need to identify the 2 points across which equivalent capacitance is to be calculated. Now in most cases, this is what will be provided to you in the question, the points about which you need the equivalent capacitance. Connect or imagine a battery between these points. So you have to imagine a battery in between those points, because then you can better visualize how the charge is going to split up or how the charge is going to flow. And the third, solve the network from the point which is farthest from the points between which you have to calculate the equivalent capacitance. So this I'll explain to you. When we do the example, I'll explain it to you that we have to start solving from the point farthest from the points where you're finding it about. So first example we have is this. So our points from about which we need to find are A and B. Which point is farthest from them? This point. So I know first I need to deal with this loop. Okay. Now in that loop, as you can see, this 3 microfarad and 6 microfarad are connected in series, which means their equivalent would be 3 into 6 by 3 plus 6, which is 2 microfarad. Now I can replace this with a single 2 microfarad, so that my circuit now looks like this. I have the 3 microfarad, which is this one as it was earlier, and this thing has been replaced with a 2 microfarad, which is the equivalent of these two. Now I see that this and this are in parallel, which means I can just add them up down. In parallel, capacitances are added up, 2 plus 3, which is 5 microfarad. This is how I find the equivalent over here. We have another example. We need to find the potential about these 2 points, the capacitance about these 2 points. Which is the furthest point? The furthest point is over here. You would say this is also the furthest point, but this is somehow connected in a similar way. We can go by the furthest point as being that. Okay. So the reason, because this point is, it's one capacitor away from B and one capacitor away from A. But this point is one capacitor away from A, but it's 2 capacitors away from B. So that is why this point becomes the furthest point. So you have to start solving from this side first. There you have 6 and 6 in series, which is going to give you 3 microfarad. 6 into 6 divided by 6 plus 6, 36 by 12 will give you 3 microfarad. Which means your circuit now reduces to this. You've replaced that 6 and 6 into a 3 microfarad here. Now this 3 microfarad is again in parallel with this 3 microfarad here, which means again you'll use a parallel combination, which is just adding up. 3 plus 3 is 6 microfarad. Your circuit now reduces to this. You just have a 6 microfarad in this part, 2 microfarad here, and another 6 microfarad here. This 6 and this 6. So this 6 and this 6 are in series with each other. Find the equivalent. Again 6 into 6 by 6 plus 6, you'll get 3 microfarad for this entire part, which means you now have 3 microfarad. You just now have, okay, it's there, it's 3 microfarad, which would be in parallel with this 2 microfarad. So the effective capacitance is just 3 plus 2 microfarad, that is 5 microfarad. That is how you go step by step. Always find the point that is furthest from the points about which you're finding the capacitance. Then see on which path that point lies, because you need to start solving from there and then slowly move towards your effective points about which you need the capacitance. Okay. So that finishes our discussion here of capacitors and how they combine in series and parallel. Thank you so much for watching. Subscribe to the channel. I'll catch you all in the next session.